Now, since we're here with stages, I haven't been time to submit a full homework yet. So I'm going to get off into certain difficulties and make some announcement about homework assignments now, because the assignments will, like that last semester for those who were here, involve a mix of MATLAB problems or problems to be worked out on paper. And so you can be submitting multiple files, like M files with MATLAB code, or maybe a scanned PDF of work on paper, or maybe someone who you might use LaTeX. So when that happens, first of all, so it's very common for students in this class to zip up whatever files they have and upload to Canvas, which is perfectly fine, but don't give me a folder hierarchy. Just put everything in one folder, whatever you have, if you're zipping them all up to send to me. I'm just gonna flatten the file structure anyway. Okay. All right, so for problems involving MATLAB functions, and I'll try to find an example. Okay. Oh, yeah, here's one right here. So a problem like this, where you're asked to write a MATLAB function, the interface to your function, and by interface I mean the name of a function, the inputs and the outputs, I want it to be exactly this. I mean, if I write it like this to give you a starting point, and it's really what I'm literally doing is giving you the first line of your function. You say in your M file, you say function, a word function, and then this exactly, so that you have exactly the inputs and outputs that I would expect. Because, as I said earlier, I reserve the right to download your code and run it myself. What I have done in some cases is I write a script that will call whatever functions you have with certain input for which I know what the output should be, and I can compare. So I can like automate the grading process. I won't necessarily do that, but I want to. But it's something that you should be prepared for. So don't give a function a different name or change the inputs and outputs. What you see here is what it should be. Okay. Let's see. Yeah, especially for problems that are on paper or you're using a MATLAB diary, make it easy to identify the problem that I'm looking to work for. Also, what the final answer is. Don't make it hard to find. Okay, some problems, of course, will involve writing MATLAB code and may have questions about that code. But in a situation like that, probably the easiest thing to do is since you're going to be looking at your M file anyway, whatever questions might be asked, you can answer them in the comments in that M file so that I can see your code and your answers all in one place. Okay, and as I grade assignments, again, I'm entering the grades in Canvas, so then in the comment box, I'll give feedback like which problems you lost points on, how many points you lost, why you lost points. In case you have any questions about that. Sometimes it happens where students forget to include part of their assignment. I guess I see promises missing, and if they did it, so in that case, just let's call it. Because if I see like, okay, you're losing like 40 points because stuff wasn't uploaded, I'll ask you about that, so that you can get credit for what you did. Okay. Also for those who were not in the corresponding class last semester, I'm lax on deadlines. And if you need more time, just take it. I mean, there's only 6 of you in the whole class, and that may result in me getting a lot of stuff done in the end, but that's why it's no big deal in this case because there's only 6 of you. Okay. So no need to keep asking me like, can I turn it in late? Yes, the answer is yes. Okay, so any questions about related to homework assignments. Yep.
So like turn in the MATLAB, like the .m file, or the like where it lists all of it?
Okay, well, I definitely want the M file. Now,
I think I'm confused about how you would turn it in. Like all together, yes, but I don't think I know how to do that.
I mean, because Canvas will let you upload multiple files, or so you can do it that way. Well, and then I can just click on each one and look at it. Or you can like have all your files on your computer and then zip them up and then upload to one zip file. Actually, it's probably easier if you don't zip them. If you just upload whatever files you have to Canvas.
Like I did last semester.
Yeah, because then I don't necessarily have to leave Canvas. I can just click on each one. Now, and then if I want to, I'm not sure about your code and I want to run it, then I can download it. But sometimes I can just grade the code just by looking. It's like, oh, yeah, I did it right, or no, this is really gonna crash. I'm not sure if it answers your question.
No, it did.
Okay, right. Okay. So now we're getting into the next section. So this is where we deviate from what you're accustomed to from ordinary linear algebra class. And we get all numerical linear algebra starting here. So to make the distinction clear about linear algebra versus numerical linear algebra, here's a quick recap of how one is normally taught to solve a system of linear equation with A is equal to B. We're still assuming that the matrix A is squared and vertical. So, our own intro linear algebra class, Math 326, here's how you would solve there. So, because what your professor is, I'll give you Dr. Harris. Yes.
I have a question about the quiz.
Yeah.
So, is it only one question?
Well,
You open
from Canvas's point of view, there's one question, but what I've entered for question is several questions. So you should see that when you open a one question.
No, I haven't opened it because if it is time limited, I'm not.
It's not time limited. Yeah. Now, if you look at the textbook, at the end of each section, there's a small subsection called concept check. And so questions are taken from there. Just so you know exactly what's on the quiz. Sometimes I leave a question out or two, but it pretty much mirrors that. Okay. Oh, that's the other thing I forgot to mention about the quizzes. Now, what you can do when entering answers for quizzes, I mean, you'll have a text box, you can enter your answers right there, or what some people choose to do is have a separate file, like a Word document or a LaTeX document, and then and type your answers in there, and then upload the attachment. So you can do it either way. But if uploading an attachment with your answers, please include the questions also. So that way I don't have to go back and forth between your document and Canvas because I have to close it and like it's this pain. But that's your questions and answers right there. That makes it so much easier. And then that's when your professors to be in a good mood with grading. Because well, all right, we're gonna be in a bad mood, but less bad. Okay. Right. But yeah, the quizzes are awesome. Okay. All right. So how Math 326 instructor will tell you how to solve a system. You form the augmented matrix, so you put A and B together in the matrix. B is an extra column. Using row operations. to get to row echelon form. So the matrix A is reduced to an upper triangular matrix U. Once you've done that, then you can use back substitution on U and the B that is been modified by the row operations, and then you have your solution and you're done. You may have also been taught to keep going with the row operations to get to reduced row echelon form, in which case that just reveals the solution. But that is actually mathematically equivalent to back substitution. Okay. Now, the thing to keep in mind is which row operations you're going to perform on A are determined, or you're applying to both A and B, but it's properties of just A that determine what row operations are. B has no role in determining like which multiple of which row you get to subtract from another row. That's an A thing. So suppose we solve A equals B, but then we want to solve another system that has the same matrix A, but a different right-hand side. So in that case, you don't want to have to go through the whole process all over again. You want to keep the row operations around. And the thing is, your augmented matrix has now changed, only in the last column, but it's still changed. So ideally, you should have some sort of record, transcript in a way, of what row operations you performed on A, in case you need to reuse them on a different B. So that's what the LU decomposition is about. Because also, we've seen that when you're solving A equals B, the Gaussian elimination part that gives you your upper triangular form, that's the most expensive part. It takes 2/3 n cubed operations or so. Anything that happens after that is order n squared work. So because Gaussian elimination is by far the most expensive, we want to only have to do that once. But the only way you can do that to be able to reuse that work on a new system with a different right-hand side, you need some way to store efficiently what happened to carry out that reduction of A to upper triangular form. So really we're going to do Gaussian elimination without involving B at all, and then we'll deal with B later. So no more using the augmented matrix. Now, before I actually get into that, I've described a situation where we want to do something differently, and that is solving several systems of equations that all have the same matrix at different right-hand sides. That may sound like some made-up situation that doesn't actually happen, but it does happen. It happens all the dang time. And an example of that you'll see later in this course. I suppose you're solving a linear system of ODEs. So something like this, and y prime is equal to jy, where j is some matrix that is independent of time. Now, we'll be seeing, when we get to chapter 12, we'll be learning about several methods for time-stepping methods for solving this ODEs like that. And some of those methods are called implicit methods, and that requires solving a system of equations where a matrix involved is based on J. So in that is exactly the kind of situation I'm talking about, where you're going to be solving that kind of system with that same matrix over and over again, right-hand side always changing, because the right-hand side will represent your solution evolving in time.
So J is the matrix of the differential operator, whatever it is.
Well, if the system of ODEs came from a PDE,
Yeah.
then yes, J would represent like a discretization
Yeah.
of a differential operator. Okay. Yeah. It's a matrix of time.
So this is what we're doing right now?
Well, this is something that we'll see later, but the fact that I just want to give an example of where that kind of situation comes up.
Okay.
Same matrix, many different right-hand sides. So it is a real thing. Because then I assume math professor would make it like, oh, what if this happens? Like, yeah, that's never gonna happen. And I try not to do that. Oh, okay. Oh, I do a fair amount of notes here. Dang, okay.
Hints.
Oh,
More hints. Yay.
oh, okay. Well, and actually, well, for homework too, there's a whole hints file,
Oh, yeah.
which I assume this is in, but there may be other hints too. Let's check that. Okay. Now, where are we at? Okay, so form a situation of just performing estimation of A1, so they're reusing information with whatever right-hand side come along. This leads to what's called the LU decomposition. There are actually many decompositions of matrices out there. We're not going to see very many in this class. In the graduate follow-up to this class, in that 610, more such decompositions come up. But matrix decomposition has been such a big deal and used so widely that approach to problem for linear algebra, matrix decomposition, was named one of the top 10 algorithms of the 20th century. Just that whole mindset of using matrix decompositions to solve problems like these. Another one of the top 10 was called the QR algorithm for computing eigenvalues, something I teach about in 610. So numerical linear algebra really changed everything into scientific computing. And this is going to be just one example of that. Okay. So, if we revisit elementary row operations, scaling rows, swapping rows, and subtracting a multiple of one row from another, we can describe all these row operations in terms of matrix multiplication. Forming row operation amounts to multiplying your matrix A, so this would be A here, on the left by some matrix E, as really just carrying out the row operation on the identity matrix. So, as an example, the row operation of interchanging the first row and the third row is equal to multiplying by this matrix that has rows 1 and 3 of identity swapped. That's kind of weird. Notice that my numbers range of matrix are kind of off kilter. That's driving me nuts. Okay. So you apply the operation to identity, you take that matrix, which is called an elementary row matrix, this is a capital E here, and that'll carry out the operation on A. Here's another subtracting 2 times row 1 from row 4. So here we have the identity matrix, and if you took row 1, multiplied it by 2, and subtracted it from the 4th row, this is the matrix you would get. So then multiplying A on the left by this matrix will carry out this row operation on A. And this is what you would get. Okay, this example is not a particularly useful row operation, but it illustrates the action. So what that means is we could describe the entire process of reducing A to upper triangular form as multiplying A on the left by a sequence of matrices, of elementary row matrices, each performing one row operation. So if we have a simple way of representing one row operation as a matrix, is it possible to represent the whole sequence of row operations by a matrix? So that is what leads us to look into what are called unit lower triangular matrices. Now we've seen lower triangular matrices. So those are all those matrices where everything above a diagonal is 0. A unit lower triangular matrix is lower triangular and all the diagonal entries are equal to 1. This matrix right here is an example of a unit lower triangular matrix because everything above the diagonal is 0. We have all 1s on the diagonal, and then whatever is non-zero below the diagonal. And the reason why it's lower triangular is when we're performing Gaussian elimination, what we're doing is, okay, we're subtracting a multiple of one row from another. But, so it's multiple of row j from row I, but we always have this situation, I is always greater than j, because we're performing a row operation in the first place to eliminate aij, where aij is below the diagonal. I is greater than j. So every operation that we perform in terms of that involves subtracting a multiple of one row from another, because we're using it to make A upper triangular, that kind of row operation is always represented by a unit lower triangular matrix. Now here's some properties of unit lower triangular matrices. So if you multiply two such matrices, then the product, so the two matrices multiplying are unit lower triangular, the product is also unit lower triangular. So in general, multiplying matrices preserves triangularity. Like you have two upper triangulars multiplying, the result is upper triangular, and so on. Inversion preserves triangularity. So if I have a unit lower triangular matrix and I take its inverse, then the inverse is also going to be unit lower triangular. Unit lower triangular matrices are always invertible. So it always has an inverse. Okay. I don't know if I assigned it in this class, but like actually proving these properties. It can be proved using a formula for matrix multiplication. But if I assign that here, I'm sorry, but I don't think I did. I think I do assign it like with 610. Oh, we'll see. But for proving it, you rely on the fact that when you have a lower triangular matrix, you have this property that the ij entry is always 0 if I is less than j. So what happens if we carry out several row operations? Now, for the time being, I'm not going to talk about row interchanging. Row interchanging mucks things up. Seriously complicates matters. We will deal with it later. But what if we're just carrying out these kind of row operations from Gaussian elimination, where we're repeatedly subtracting a multiple of one row from another? So we're trying to eliminate the ij entry to A, where I is greater than j. So we compute this multiplier, mij. So then what happens is, like, here's your A, and what's the first entry you eliminate? The entry in row 2, column 1. And then you go to row 3, column 1, or 4, column 1, and so on, all the way down to the bottom. So here's row operations to eliminate all the way down to A and 1, so the last entry in the first column. So all of this that I'm highlighting works on the first column. So now that column is entirely 0 except for the first entry. Then you move to the second column. You eliminate the entry in row 3, column 2, and so on, down to the bottom. And you keep going until in the end, you have, this is your last row operation. That's the last row, row n, and then the second to last column, n minus 1. So what you're doing, you're taking A, you're multiplying it by a whole sequence of unit lower triangular matrices, and getting this matrix U. And because of the properties I've shown you, we know that the product of all of these matrices is also unit lower triangular. But beyond that, we don't know anything else about what this matrix, not yet. Now, I'm going to write this a little more concisely. I'm going to call M1 the matrix whose job it is to eliminate all the entries in column 1 below the diagonal. And then M2 eliminates the entries subdiagonal entries from column 2, so forth, all the way to column n-1. So this product right here is the same as this product. It's just that matrices that are working on the same column of A, I lump together. And that's what I show here. Each one of these M's is a product of several of these E's. So we started with the entry right below the diagonal entry, row J plus 1, then J plus 2, all the way down to the bottom. So this is all the work that's done on column J. So we'd like to know, what does that matrix look like? Questions up to this point? Okay. Now, so these entries, each one of these, the E's that make up this M, all of them are equal to the identity matrix, except for the negative of a multiplier in row I, column J. Why negative? Because we're subtracting the multiplier times row J from row I. So we have this multiplier sitting in the IJ position. Now, so here's an example. This matrix is meant to eliminate the 2-1 entry using a multiplier of -3. This matrix is meant to eliminate the entry row 3, column 1 using a multiplier of 1. This matrix is meant to eliminate the entry in row 4, column 1, multiplier -2. So multiplier is -3, 1, -2. And they're written in this order because this operation is carried out first. We're multiplying this with A, and then the result of that we multiply with this, multiply by this. And what happens when we multiply all these things together? It works out very nicely. All it does is we still have identity on the diagonal, and then all the multipliers are just stacked on top of one another in column 1. So, in fact, knowing what the row operations are in these E's makes it very easy to get this matrix MJ. Now, I'm not going to go to trouble proving that. If one needed to prove that, it would come from the formula for matrix multiplication. But so we know, once we know the multipliers, we know what these capital M matrices look like. We just take the multipliers and fill them in column J, whatever J is. So that part works out very nicely for us. And on top of that,
Why did we do that?
what?
Why did we do that? Multiply all these together?
Well, because that's what's happening is that A is getting multiplied by all of these. Because what we want to do is understand what this entire product is. But as an intermediate step towards that, we're going to understand what happens with one column at a time. Right. So in other words, eliminating all the entries below diagonal in column 1 amounts to multiplying A on the left by this matrix, where we take those multipliers and just put them in, like, whatever entry we're trying to eliminate, we put its multiplier in that position. Now, as mentioned earlier at the beginning, we want some sort of record of what row operations were performed. Well, for column 1, this is that record. That what happens is these are the negatives of all the multipliers that we use on column 1. Now, what also works out nicely is the inverse. So if I take this matrix, it's unit lower triangular, so I know that its inverse is also unit lower triangular, but I don't know anything else about it. But it can be shown, I won't go for trouble here, but it can be shown that if I want the inverse of this matrix, it's just this. What's the difference between them?
The combination.
Yes. Yeah. So in fact, the inverse, so whatever matrix you use to eliminate all the entries below the diagonal in column J, the product of those matrices that perform those operations as a unit lower triangular matrix with the negative multipliers in column J. But the inverse of that has the multipliers themselves not negated in column J. Now, soon we'll see why that's very helpful to actually have the inverse. So, what's happening is, when I start with A, and I apply all these M matrices to A to eliminate all the entries below diagonal, then, okay. So I have all these matrices times A is equal to U. But all these matrices, these M's, they're invertible. So what I can do is I can move them to the other side. So another way of looking at this is A is equal to the product of the inverses of all of these matrices, these M matrices, times U. Now if I take M1 inverse and I call that L1, then I can write my equation this way. A is factored into a product of all of these L's times U. Now, each of these M's, M1, M2, etc., is a unit lower triangular matrix. Their inverses are also a unit lower triangle. Therefore, a product of all of these, also a unit lower triangle. Now, all of these L's, we know what they look like. They look like this. So, as part of this example, I can identify the matrix on the left as the inverse of M1. I'm taking the inverse. And so in the notation that's down below, this matrix, the inverse, I'm calling L1. And it's 1 because this matrix comes from applying row operations to eliminate entries in the column 1. So we've seen what happens when we take individual row operations that are working on the same column and multiply them all together to stack some multipliers in that column. But what happens if I have a bunch of matrices like these, like this one for first column and a similar matrix for second column, and so on? What happens when I multiply all of those together? It turns out that's going to work out nicely too because of the unit lower triangularity. So at this point, I have A written as a product of all of these L's times U. So now I'm going to define capital L to be the product of all of those. And what ends up happening is, when I multiply all of these together, the final matrix, capital L, all it is the identity matrix along with each multiplier Mij in the ij position within the lower triangle. So in other words, if I take this matrix, well, if I have this matrix, the inverse for column 1 where we already no longer negated, and then so this matrix is column 1, and then I multiply the matrix column 2, it's just going to take all multipliers and stack them next to each other. So this leads to what is called the LU decomposition, also known as the LU factorization of A. So, and this decomposition is given to us by Gaussian elimination. So all we have to do to get this is none of the stuff I was just showing you, thankfully. It's easier than that. What you can do is you carry out Gaussian elimination on A, that will produce U naturally, that's the result. But as you do at that, you can, as you compute each multiplier, Mij, you store that in the ij position of your matrix that you're working on. So what happens is, you can actually store, even though I've written A as a product of two matrices, you can actually store them in one. Why? Because U is upper triangular, and L is unit lower triangular. We know the diagonal entries are all one. We don't need to store them. The interesting part of L is below the diagonal, the multipliers. What it do is, yes, so you can start with matrix A, your Gauss elimination function, and then overwrite A with the information that comes from L and U. So the upper triangle, including the diagonal, will have all the elements of U, your result of Gauss elimination. The lower triangle, you stuff all the multipliers in there, and you're done. You have your LU decomposition. And so it can be stored very efficiently because you can pack two matrices into one. And in fact, in homework 2, that's what you'll do with Gauss elimination, is have it return just one matrix that has key information about L and U in it. All right. So then, once we've carried out this decomposition, and now we want to solve A equals B, because at this point we've done nothing with a B. We don't even have a B. But once you have a B, you can use the multipliers that are stored in L, and that those tell you what row operations you now need to perform on B that you already performed on A. You can do that with whatever B's you get. And that's going to be a lot less expensive than the Gauss elimination you just carried out. Any questions about how this LU decomposition came about? There was a lot of matrices flying around here. But to recap, if you think of Gauss elimination process this way, all the row operations that we needed, what we have in each column is condensed into the M's. And really what we're doing is, all we're doing is we're taking all this and moving it to the other side because we know it's invertible. And because we know what the inverses of each of these individually look like, and we also know what happens when we multiply all those inverses together, that ends up being a unit or a triangular matrix. So really, the LU decomposition comes about from taking this equation, moving all the elementary row matrices to the other side, so that you have A equals something, and we can work out what that something is. Yes?
So in other words, matrix L is an identity matrix, but all the entries below the main diagonal are the multipliers, but they're
Yes.
positive. But not positive, but they
not
have negative.
Yes. What do I have that in here? I didn't have that in the notes to show you. Okay. Okay. Yeah, this is what one of the M's looks like, just in general, where you have the negated multipliers sitting below the diagonal, and you have ones on the diagonal. Everything else is 0. And then, yeah, so then the inverse, same thing, except the negatives are gone. Oh, yeah, so this is what a typical L looks like. 0's above a diagonal, 1's on a diagonal, multipliers below a diagonal. So in deriving L, I'm having all these operations performed, like I'm taking these matrices and multiplying them and inverting them and all that. you don't actually have to do any of that because we know what the final L is supposed to be. So, so really you're not even computing L, you're just storing the stuff in it because you're computing the multipliers during the Gauss elimination process anyway. So what I've just shown is that and then that A can be factored into L times U, where L comes from inverting all of the elementary row matrices that are used to compute U, and then times U itself. So A can be factored into a product of a unit lower triangular matrix, L, times the upper triangular matrix U. And that's what enables us to perform Gauss elimination just once, and then repeatedly use the resulting row operations on whatever right-hand side B we get, however many there are. So L really serves as this transcript in a way of what happened to produce U. Because we have the values of the multiplier stored there, and the position of each multiplier tells us what the row operation was. For example, if you have some number in the 3-2 entry of L, then what we know what happened was you subtracted that multiplier times row 2 from row 3. So it's a position and numbers themselves that that we can get this transcript of how Gauss elimination proceeded. So now if we have the LU decomposition, how do we actually solve AX equals B using? So starting with solving AX equals B, but then I know that A is equal to LU if I've just done Gauss elimination. So now I have LUX is equal to B. So what I do is I introduce a new variable Y. So I have I define Y to be U times X. Now I don't know what X is. X is what I'm trying to get. So I don't know Y either. What I do know about Y is it satisfies this system of equations. Ly equals B. So once I carried out the LU decomposition, now I solve this system of equations. Now, this is equivalent to applying all those row operations to B. We're just looking at the point of view of solving the system.
Why would it say Y equals UX?
To break down the process into simple steps. Because by substituting LU decomposition, now I have this.
Mm-hmm.
But if I'm going to obtain X, I need to invert both of these matrices. But what happens is, if I simply call this Y, then I know how to get it. So I have L and I have B. But here's the whole process. Maybe I'll clear it up. So first, we do Gauss elimination. That gives us the LU decomposition. Here's how much work it took: 2/3 n cubed operations, the most expensive part. Then I solve this system, Ly equals B. So this is how you apply the row operations to B. So Y is the modified B that you get from performing those row operations. Now L is a unit lower triangular. So because it's lower triangular, you use forward substitution. And that takes n squared minus n operations. But minus n here is because L is unit lower triangular, so we don't have to divide by diagonal entries. So this is a step that's being performed to modify each element of B. That's similar to what's done using Gauss elimination. Because Lij is Mij. So really, I mean, this is what you see the algorithm for forward substitution. But really, these two are saying the same thing. Now we take into account how I define y. Y is equal to u times x. Y is now known. So I can solve this system of equations, ux equals y, for x. And u is upper triangular. So I use back substitution. That takes n squared operations. And now I have x. So the LU decomposition took solving this complicated system and broke it down into two much simpler steps. It just took a lot of work to get that decomposition. So now we have our process for solving ax equals b. And if we now have to solve the same system with a different right-hand side with the same matrix, I don't have to carry out step 1 again. I have LU. I just need to do steps 2 and 3 that are a lot cheaper. So questions about this process? Now, I should point out though, since I said that I wasn't going to do anything today involving row interchanges. The LU decomposition is not always exist, and that's something I'm going to do later. Well, I showed an example last time where I made a matrix where it was absolutely necessary to do a row interchange just to keep Gauss elimination going. So that's something we'll talk about. Actually, I think in the next class or surely we'll after that. Okay. So this is the numerical universal way of solving ax equals b. Because I don't think they teach anything about the LU decomposition in Math 326. It might for all I know, but it's expensive to teach it. Okay, I need to take a look at what problems I assigned for homework 2. Oh, okay. Oh, quite a few. Okay, and here are the hints. Oh, I do have the proof about if you multiply two matrices that are lower triangular, the result is has the same triangularity, and then also the inverse. Okay, so the hint I have in the notes is actually for this problem, but it's also written in here. Okay. Oh yeah, let's do a type 1 problem. This problem will be a pain. I'll cover pivoting first. That's why there's a lot of hintage. So definitely want to go through this. Okay. Oh wow, yeah, a lot of this. So apparently there's 2 really painful problems here. The rest aren't so bad. Well, we'll see. This is why I don't enforce deadlines. Yeah.
Can you go back to the file, your notes?
Yeah.
Yeah, here.
Yeah.
So here, well, I'm not looking at the hints now, but for the algorithm, are you assuming that your U is an upper triangular matrix?
Yes. Yeah, just because that's what Gauss elimination will produce.
Yes.
Okay, I do want to talk about one of the problems from that homework. That's one of the more simple ones, but for MATLAB. Okay. Find it here. Oh. Okay. So here we have the algorithm pseudocode for forward substitution, assuming a unit lower triangular matrix. So this won't work for a general lower triangular matrix, only for a unit one. And then there's a expression here that's assigned for homework to write this function of forward substitution. Oh, there's a typo. Wait. Oh, did I fix the typo? Oh, I guess it did. Well, this is my PDF version of the book where I made a fixed mistake. So when you printed, if you have a hard copy of the book, it might say forward sub ly, but it should be b. Okay, so you have to write a MATLAB function that implements this algorithm. And then I tell you to test it. Always test your code. And I want to say a little something about that. Okay. How do you go about testing forward substitution? Because it's only valid for solving the system where the matrix is unit lower triangular. So you need a unit lower triangular matrix. So I'm going to show you how you, because sometimes you're writing an algorithm that's intended for a certain type of matrix. So you need to create that type of matrix for testing it. So I can show you how you do that in this case. So first I'm going to create a random matrix. Okay, now of course this won't do. It's not even lower triangular, let alone unit lower triangular. And then what I'm going to do is I'm going to use a function called try_L. So try_L extracts the lower triangular portion of a matrix. But actually, I don't want the diagonal either. I want the diagonal to be 1. So actually, I want to take everything that's strictly below the diagonal. Now, if I do just this, that will give me the lower triangle including the diagonal. But since I don't want that diagonal either, I'm going to add a second argument, -1. Now, the way MATLAB identifies diagonals, the main diagonal is diagonal number 0. Diagonals above the main diagonal are given positive numbers, so first diagonal, second, third. Diagonals below the main diagonal are given negative numbers, so diagonal -1, -2, -3. So this command right here is going to give you what I want. That it wipes out everything above and including the diagonal, keeps everything below it. So in general, try_L LD, where D is optional, keeps everything on diagonal D and below it. Alright, so positive D equals above the main diagonal, negative is below. There's a similar command, try_U, for extracting the upper triangular portion of a matrix. So if you do something involving an upper triangular matrix, you can use that to create one. Now, I still need ones on the diagonals. What I'll do now is add. EYE is a command that gives you an identity matrix. In this case, we want a 4x4 identity matrix. So I'm just going to add ones to the diagonal. And now L is unit lower triangular. And then what I can do is I need a V. So I'm going to create a random right-hand side vector, a column vector, 4 entries. And then I'll compute the exact solution. And for that, I'll just use MATLAB's / function. Okay, so that'll give me, this is the solution that I'm supposed to get. And now I have the function forward sub in this folder. I'm not gonna show it to you because I assigned it homework. So I compute the solution using it. Of course. Which is diary it does. Okay, so now I call my function to give me y2 as the output. Same L, same B. So these should match. They appear to match, but I want to make sure. So, this is a concept from last semester, relative error. So what I can do is I can take the norm of the difference between these two y vectors divided by the norm of what I'm treating as the exact solution, so y1, and this ought to be small. Wow. Yeah, it's small. Now that doesn't normally happen. But I could also that was called the residual. B minus L times y2, because L times y2 should be equal to B. So this also could be small. And yeah, it is. So the order of 10 to the minus 16. Okay, so this is an example of how you test your code. Just give yourself data that satisfies whatever assumptions are needed. In this case, we had to have a matrix that was unit lower triangular. And then if you're able to solve a problem using something that MATLAB already has, like to give you a reference solution to check against, then you can use norm compare to. Norm is a magnitude of a vector or a matrix. That's what that function does. We'll talk about norms later. But for vectors, it's equivalent to what you learned about like in calculus 3, where it's for vectors, it's square root of the sum of squares of the elements of a vector. So nothing too unusual here. But for matrix, it's a bit more complicated. Okay. Now, I actually have 2 more class periods to spend on the LU decomposition. There's a lot to cover there. But I've come to the end of notes for today. So, do we have any last questions about anything?
Nope.
All right. Well, I guess I think that